Hello everyone. Today we'll continue our discussion of bases and talk about a couple of important related concepts, dimension, rank, and what I'll call uniqueness of representation, which we'll get to at the end here. This will lead us into the notion of a coordinate system, which will be the focus of our piece of our lecture next time. So let's first suppose we have W is a subspace of a vector space V. So W itself is a vector space, and often we'll take W to equal V. So, think of a subspace of Rn or something like that. In particular, you could have the column space of a matrix, right, which is a certain subspace of an underlying R to the M, I guess we usually say. But here's the fact that I want to mention here, is that the size of any basis for W is always the same. So the size, when I say the size, I mean the number of vectors. Remember, a basis is a collection of vectors with the two properties of linear independence and span. And what I'm saying is if in general, there'll be many bases for a given subspace. We've seen that already. But any two will have the same number of elements. So in particular, what I mean here is if B is, let's say, B1 through BP, and let's say B prime is, I don't know, C1 through CQ, then, well, if these are both bases, are both bases for this subspace W, then P equals Q. So the number of vectors in each collection has to be the same. So we've kind of already seen this, in the background of our discussion already. So let me give an example, a familiar example here. What are bases for Rn? So last time we saw that these are the same as they're given by columns of an n by n invertible matrix. Okay, so remember last time, if I want to get a basis for Rn, I can take any invertible n by n matrix, take its columns, and vice versa, right? Every basis for Rn comes about that way. So in particular, every basis for Rn will consist of n vectors. And this leads us to the next definition. So definition, the size of any basis, so the number of vectors, is called the dimension of W. And okay, so in particular, we were just talking about Rn, and we always know that any basis has n elements, so maybe this is not too surprising, but Rn, the vector space Rn, has dimension n, right? And that's hopefully intuitive, right? The number of coordinates in any vector in a vector in Rn has n entries, and that's how many I need to describe any vector, and that's kind of our idea of dimension. Okay. There's another important example that we've seen already. So suppose A is an m by n matrix. And what did we see last time? Well, let me suppose that A has R pivots in its echelon form. So whenever I say pivots, I mean in the echelon form. So what I'm saying here, of course, is that I've got this matrix A. I don't know what it looks like, but I row reduce it to echelon at least, and I get, maybe there's a pivot here, and a pivot here or something. Okay, so what we saw last time is that the column space of A, so call A, this has dimension R, because remember we saw last time that if I want a basis for the column space, I take the columns of the original matrix corresponding to the pivot locations of the matrix. If there's R pivots, then I'll have R elements in that basis. And the null space of A has dimension, well, remember when I describe the null space, I get a vector in the basis for every free variable. And if there's n variables, right, and R of them are pivot variables, and there's n minus R free variables. So this number R has a name. It's called the rank of the matrix. So it's the same as the number of pivots, right? And this also has a name, this number n minus r. So r is the rank. N minus r is sometimes called the nullity of A. I'll probably use that a little bit less, but that's just the dimension of the null space, which, like we saw, is always n minus r. So the rank plus the nullity equals n. That's something you'll see a lot. Note that rank plus nullity equals n. Okay. So changing gears a little bit, I want to discuss one more important result that, well, tells us why we might care about bases. So let me call this a theorem, so we're kind of changing gears a little bit. Here's a theorem I want to mention here. So suppose, let's say B is B1 through B, I don't know, let me say Bm is a basis for a vector space, let's call it V, and let's say X be any vector in V. Okay, so you've given me a basis for the vector space V, and then you give me an arbitrary vector X. So it turns out then there exists unique weights, let's say C1 through Cm, such that I can write X as a linear combination of the basis elements with those weights. So such that X equals C1 times the basis vector B1 plus C2 B2 plus Cm Bm. Okay? So this is kind of cool. This is saying that if you have a basis, so you fix this basis for your vector space, then if you give me any vector in the vector space itself, I can write it uniquely in this way as a linear combination of those basis vectors. So why is that? I can prove this for you, or at least sketch a proof. So first of all, remember what a basis is. So remember, if you have a basis for a vector space, it has the two properties. First of all, it is a linearly independent collection. And then the other thing is that it spans, right? So to say that the collection spans the vector space V means that any vector can be written as a linear combination. So the first thing to notice is the fact that such a representation exists follows from the fact that V equals the span of B. Because remember, what that means is that, by definition, to say that V equals span B means that any vector in V can be written as a linear combination of these. So what do we actually have to prove? We have to prove that there's this unique property, that there's one and only one, right? We know that there's at least one now, but so we need to show why is this representation unique. Well, I'm going to argue by what's called contradiction. Suppose we had another representation. Suppose we had X written as, I don't know, D1 B1 plus D2 B2 plus ... dm bm. So this is like a different way to write, so I want to show that this was the only way to write the vector X, but maybe there was another way to do it. So what I'm going to do now is subtract, this guy, I'll subtract, I guess, the double star from the single star. So subtract, I'll just write star minus star star. And what do you get? Well, the left-hand side is x minus x, right? So that's the 0 vector. And then what do you get here? This is C1b1 minus D1b1, which is the same as C1 minus D1 times the vector b1. Plus, the next thing is C2b2 minus D2b2. So that's going to be C2 minus D2 times b2. I keep doing that, ... The last guy, ... I guess. The last guy is Cm minus Dm. Right, Cm minus Dm, which becomes Cm minus Dm times the vector Bm. Sorry to cramp you out there in the corner. Now, what's the punchline now? Well, what do I have here? I have the vector 0 written as a linear combination of the vectors b1, b2, bm, right? This is something times b1 plus something times b2, etc. But what do we know? We know that this collection B is a basis, therefore it's linearly independent. So, but B is a linearly independent collection. So what that means is that, remember, the only way to write the zero vector as a linear combination of a independent set is when all of those weights are 0. So this implies that C1 actually equals D1. This is 0. C2 equals D2. That has to be 0. And all of these are, dot, dot, dot. They're all the same. So Cm equals Dm, which means that this, this new representation that you gave me was not new at all. It was actually just the same as the one you gave me. There's one and only one way to do that. So this, which proves the claim. Okay, so that's the proof of that fact. And let me just again reiterate what we proved. We showed that if you give me a basis for a vector space, there's one and only one way to write a given vector as a linear combination. Okay, so that's going to be an important fact that we'll use next time when we talk about coordinate systems. I should maybe just say that, this shouldn't be too surprising, again, if you're thinking about, say, the standard basis for Rn, right? That's clear that I can write any vector as in a unique way. So let me just maybe end with e.g. the standard basis, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the standard basis for R3. If you give me any vector, say, x, y, z, let's think this way, then how do I write it as a linear combination of these things? Well, it's sort of obvious, right, that there's one and only one way, because if I want to get x in the first coordinate here, well, I better put an x as a weight of this first vector. If I want a y in the second coordinate, then the only thing that contributes is this vector, so I better put a y, and similarly, this has to be z. So, again, this is clear in the standard basis that this property holds, and the magic is that it also holds for any basis. Okay, so that's it for now. We'll continue next time with more representing vectors. See you then.